So, dear colleagues, now we open next stage of our sessions. So I want to introduce TC Chi of 304, Professor Kiki Poon. He is a full professor from National University of Singapore, and he will be introduce about contents of lecture. So lecture name of Suzanne Lacasse lecture. So please, Professor.
Good evening to everybody. It is my pleasure to introduce the Suzanne Lacasse lecture. This is an honor lecture that is hosted by TC 304, Engineering Practice of Risk Assessment and Management. I believe Suzanne should be somewhere in the audience. Suzanne, I wonder if you could just stand up and let everybody recognize you a little bit. I'm sure everybody knows that. And also allow me to thank ISSMG, particular President Roger Frank, for his very nice support, and the organizing committee for allowing us to have this lecture in 19 ICS MGE. A TC 304 honors Dr. Lacasse for her pioneering contributions to risk management for geohazards, and her contributions is particularly impactful to practice. She was a managing director of the Norwegian Geotechnical Institute from 1991 to 2011. And Dr. Suzanne Lacasse has delivered the 37th Terzaghi lecture in 2001, the 8th ISSMG Terzaghi oration in 2013, and the 55th Rankai lecture in 2015. At this point in time, just for your information, this would be the third. The first was delivered by Professor von Griffiths in Shanghai. I believe he's in the audience as well. And the second was delivered by Professor Gregory Becker in Denver this year. So with that, maybe I will pass it back to Professor Askar.
Thank you, Professor Kiki Poon, for your kind introduction. So, dear colleagues, I also remember about activity of Professor Suzanne Lacasse, 2007. So she visited Yuzhno-Sakhalinsk, very long distance, and giving lecture about disaster prevention. So now it's time coming to introduce of our lecturer, Farok Nadim. So Farok Nadim is a representative of Norwegian Geotechnical Institute of Norway. So he is educated at Sharif University of Technical 1977, received of bachelor degree in structural engineering, and also master science degree in civil engineering MIT 1980, and also doctor of science in civil engineering and also MIT 1982. So now is a little short information about his career. So he was the senior engineer of Norwegian Geotechnical Institute 1984-2002, and adjunct professor of TNU and University of Oslo 2004-2014, and also director of International Center for Geohazards 2003 and 2012, and also now is he work technical director of Norwegian Technical Institute, Norwegian Geotechnical Institute since 2013 and present time. So I invite to podium of Professor Technical Director of Norwegian Geotechnical Institute, Farok Nadim.
Well, thank you very much for the kind introduction, Mr. Chairman, and thank you, ladies and gentlemen, for staying this late in the afternoon for the last lecture of the day. I first got to know Suzanne in 1978 when I was a graduate student at MIT. And I've worked very closely with her since 1982 when I started at NGI. Actually, on Monday was exactly 35 years since I first started at NGI, and almost my whole career at NGI, I've been working closely with Suzanne on some project or another. So in my presentation today, I will go through a few case studies, which all of them Suzanne has been involved either directly or indirectly. And I will try to convince you that reliability-based approach is a good way to go if you want to have a robust geotechnical design. What is risk? Well, risk is one of those abstract terms that many disciplines feel ownership to it. So it has many different definitions in many different disciplines. Our international society, ISSMGE, we have a glossary of risk management terms, which defines risk as a measure of the probability and severity of an adverse effect to life, health, property, or environment. In 2009, the United Nations Organization for Disaster Risk Reduction, they came up with the terminology of disaster risk reduction terms. And in their terminology, risk is defined as a combination of the probability of an event and its negative consequences. So it's very similar to the ISSMGE definition. But in the same year, ISO published a glossary of risk management terms. And they came up with a very interesting and kind of a cryptic definition of risk. In ISO's definition, risk is the effect of uncertainty in objectives. And an effect could be positive or negative. It's just a deviation from what you expect. I think this is a very interesting definition, and it drives home the point that if you have no uncertainty, then there's no point to talk about risk. Risk is closely associated to uncertainty. And dealing with uncertainty is kind of a day-to-day work of a geotechnical engineer. In any sort of geotechnical or geological assessment, one has to do with uncertainty, either implicitly or explicitly. When we're doing geotechnical design, no matter what design approach we use, the safety philosophy is that the risks associated with the design should be so low as to be considered negligible. Now, as engineers, we look at risk as a function of a failure probability and the consequences of failure. So to achieve a robust and safe design, we must ensure that the probability of failure of the component or the structural system that we're designing is tolerably low under the applied loads. I think this point that I'm trying to show in this figure was also mentioned by Professor Day yesterday, that safety factor is not a good measure of safety because it doesn't tell you anything about the uncertainties. Consider two situations where for both situations you're calculating a safety factor of 1.5. But in one case, there's a lot of uncertainty about the loads. There may be dynamic loads, there may be environmental loads. You're not sure about the drainage conditions. You have very bad site investigation data. You're not sure about the soil properties. So if you assess the probability distribution function of your safety factor, you end up with this red distribution function. In the second case, there's very little uncertainty in your loading. It's mostly static loads, which are well known, and maybe you have very good site investigation data, you have very much experience with that area, so there's very little uncertainty in your calculations. Then in the second situation is this blue curve which represents your factor of safety. Probability of failure is the area of this distribution function where your safety factor is less than 1. So for the blue case, it's this area here which represents the failure probability. For the red case, it's this area here. So you can see that even though in both cases you're calculating safety factor of 1.5, one case might have 10 times greater probability of resulting in a bad design with failure. The design approaches that are used in geotechnical engineering, traditionally we've been using the working stress design, which is based on an overall factor of safety, and that lumped factor of safety is going to take care of all the uncertainties. The more modern design codes are based on the load and resistance factor design. It's called LRFD in North America, and it's called characteristic values and partial safety factors in Europe. In this approach, you try to apply a different safety factor to the different components of resistance and load that enter into your design equations. And these partial safety factors represent the relative uncertainty in these different components. Now, reliability-based design kind of jumps over this safety factor business and goes straight to calculating the failure probabilities and reliability index. It's more rigorous, it's more complete, and it accounts for the uncertainties explicitly in a direct manner. In the jargon of the reliability-based design, the working stress design is called the level 1 approach. LRFD is called the level 2 approach, and an explicit calculation of failure probability and reliability index is called the level 3 approach. And the whole concept is that, as we all know, all predictions are subject to uncertainties. And because of these uncertainties, it's not practical or economical to assure absolute safety. So when we talk about safety or serviceability, we can only talk about these concepts in a probabilistic term. So the objective of reliability-based design is try to keep our probability of failure, which is the probability, in simplified terms, the probability of resistance being less than the load, to be less than the target value. The design risk is quantified by this target value and failure probability, but the main challenge is that we should make a conscious choice of this target failure probability. Most people don't want to admit that there's any probability of failure related to their design. But if you want to do RBD, then you have to set a target value for your design. When we're doing deterministic design, this is basically what we do is look at all the available soil data and then choose a characteristic soil property, characteristic soil profile. We look at all the loads, pick up characteristic loads, one specific number. Our geometry is deterministic. We feed all this information into a model, and out of the model comes a safety factor. We compare it with an acceptable safety factor. If what we've calculated is greater than the acceptable safety factor, then we have a good design. So if the acceptable safety factor is 2 and you calculate 2.01, you're a hero, and if you calculate 1.99, you get fired. A probabilistic approach is basically that you go through the same steps, but instead of picking up a characteristic profile, characteristic numbers, you describe the uncertainty in all your inputs in form of probability distribution functions, or at least in terms of means and standard deviations. Then you feed all these things into a model, but your model, you realize it's an idealization, it's a mathematical idealization, so the model also has some uncertainty in it. And out of your model comes a distribution function of a safety margin or a safety factor. And then from that, you estimate what's the probability of failure or what's the reliability index. And your acceptance criterion is that your reliability index is greater than the acceptable value, or your failure probability is less than the tolerable value. So what should we do in terms of calculation of failure probability? Well, the first step is that we have to establish a precise definition of failure. Once you've done that, then you can apply a number of methods for calculating failure probability. Maybe the simplest one is the first order second moment approach that gives you the mean and standard deviation of whatever performance measure you're interested in. And then you make an additional assumption, and from that mean and standard deviation, estimate your failure probability. Monte Carlo simulation is some sort of a brute force approach that can be applied to any type of problem where you have a mechanical model for it. But it does have this disadvantage that if you're dealing with a good, robust design, you often have very small failure probabilities. So if you're dealing with a failure probability of the order of 10 to the minus 4, 10 to the minus 5, you have to do hundreds of thousands or even millions of simulations to get a good statistic to establish that failure probability. That's why the first and second order reliability methods, so-called form and SORM, are becoming more and more popular. They're the sort of approximations that give you a very relatively precise approximation of low probabilities. They're relatively easy to use, and they give you a lot of additional information along the way, which in many cases, they're more valuable than the calculated failure probabilities. In some classes of problems, we really cannot develop a precise mechanical model of the problem and assess the failure. But we still can estimate the failure probabilities through judgment, discussion with experts, and I give you one example of this thing where an event tree analysis approach is used. It's very popular for dam risk analysis, especially for existing dams, for tunnel risk analysis, and all types of major infrastructure that you might be interested in. So I'll give you a couple of examples of application of reliability-based design for foundations. The first example is design of offshore pile foundations. The motivation for this type of study is that recently the API and ISO guidelines for offshore design, they allow for the use of newer CPT-based pile capacity design methods. And these newer methods, they haven't really been tested in practice over many years. So API and ISO do not tell you what sort of partial safety factor you should use when you use these methods. The only thing they say that it's up to the engineer to select an appropriate safety factor when using these CPT-based methods. Now, this is not very helpful for a design engineer. So you can, in practice, you can choose to either be conservative and use a very high partial safety factor in using these methods. Or you can try to assess the safety level by calculating the annual failure probability and comparing that with what is the goal in these codes. We did 3 studies for an oil company in Norway for 3 different jackets that were being designed. All 3 jackets were in almost 100-meter water depth. The piles were similar. Each pile was about 2.5 meters in diameter, and the wall thickness varied between 90 and 100 millimeters. The API and ISO codes, they allow for 4 CPT-based design methods: the Imperial College method, NGI method, UWA method, and Fugro method. Now, if one were using the API method, then one could have used the resistance factor of 1.3. But the owner of these platforms, the operator of these platforms, to make sure that they have a safe design, they require the resistance factor of 1.5. And that resulted in pile lengths that were, in some cases, impossible to drive through that soil profile. So then they asked NGI to do a reliability-based assessment and find what pile length gives us an annual failure probability less than 10 to the minus 4. That value, annual failure probability less than 10 to the minus 4, is basically the Norwegian law. That's a requirement for offshore structures on the Norwegian continental shelf. I'm not going to spend too much time on this figure, but the basic concept is that if you have uncertainty in your load, this is represented by this curve here, and you have uncertainty in your resistance. Let's say this red curve represents the resistance. The failure probability is a function of the common area under these 2 distributions. So the further you push this resistance curve, or the probability distribution of your resistance to the right, the smaller becomes your failure probability. If one were doing a LRFD design, then we had to choose a characteristic value and characteristic load, and then apply appropriate safety factors to them and make sure that the load times the partial safety factor for load is less than the characteristic capacity divided by the partial resistance factor. It shows you the variability in the data that we have. The plot on the left shows the end-to-end shear strengths in the clay site. And you have all those dots there, which are the in situ measurements, and some of them have been interpreted from CPT. And the red curve, this one here, shows the mean value of the end-to-end shear strength, and the 2 dashed red curves show the standard deviation about the mean value. The black curve here shows the characteristic profile that was picked up by the design engineer. Forget about this blue curve. This is kind of a reference curve that shows if you had a normally consolidated clay, this is what you would have expected. So it's a heavily over-consolidated clay at the top layers at least. The one on the right shows the cone penetration resistance for the sand sides. And again, you have the mean value plus minus 1 standard deviation. Notice that in some of these places you have these dots here. At these locations, the resistance was so high that the cone couldn't penetrate more. So the actual resistance is more than what's shown on that plot. For the 4 different CPT-based methods plus the API method, if we do deterministic calculations, we get a range of capacities with depth. This is for the clay side. This one is for the sand side. And as you can see, depending on where you put your partial safety factor, you may, at least in this site here, you may stop here or you may miss that value and then you have to go much, much deeper. So it's, for an engineer, it doesn't really make sense that your depth could be that sensitive to what you use as partial safety factor. But it's not just the uncertainty in the capacity which is governing this thing. There's a when you're designing an offshore foundation, there's a very large uncertainty in the environmental loads. So it was important for us to get a good grip on the uncertainty in the environmental loads that come into the picture too. And then for that, we had to, it forced us to have a very close dialogue with the structural engineers and the hydrodynamic experts. But just to make a long story short, by doing this reliability-based design with the target of having the probability of failure less than 10 to the minus 4, in the clay sites, the pile lengths were reduced from 90 meters to 75 meters. In the sand sites, they were reduced from 51 to 27 meters. And in the mixed site, from 45 to 36 meters. So this represented huge savings in close to maybe millions of dollars at each of these locations. Of course, our client was very happy to accept these results because it meant huge savings for him. But if we were coming up with the opposite conclusion, if the reliability-based design was giving us pile lengths which were longer than the deterministic design, I'm pretty sure they would have ignored our calculations completely and just said, okay, we're happy with the deterministic design. Second example I'm going to give you is from a dam risk assessment using the event tree analysis. And the dam is actually, it's only 29 meters. It's not a very large dam. It's a rock-fill dam in western Norway called Drabladalen, so it's not very easy to pronounce either. But it's a very interesting case study. This is the cross-section of the dam. It was built in the early 70s. The dam length is about 800 meters, height about 30 meters, reservoir volume 58 million cubic meters, and there's a moraine core, as you see this zone 1 here, and then a filter zone, and the rest of it is rockfill. And Norwegian rockfill is very high quality rockfill. So in terms of stability and issues with stability of the dam under different loading conditions, this is a very robust and safe dam. But when we did the reliability analysis of this dam in 1996, and the reason the owners of the dam wanted to do it in 1996 was that there was a lot of interest in dam risk analysis in those days. And they wanted to acquire knowledge about what additional information, what sort of added value that can be gained by doing this sort of dam risk analysis. Then we redid this same dam in 2016, because for about 15 years there was absolutely no interest in this thing. But again, in the last couple of years, there's been a lot of interest by dam owners in Norway and also in US and Canada and other places in doing dam risk analysis. The reason they did it in 2016 was this renewed interest, but they, in the meanwhile, from 96 to 2016, they had done a number of rehabilitations on these dams, so they wanted to quantify these effect of these rehabilitations. And the dam owner also wanted to compare the reliability of the dam with what's international standards for other large dams in the world. Sort of event tree analysis is a graphical method that goes through a scenario of what happens if type of analysis. So, usually you start with some triggering factor, for example, an earthquake. And then you see how that initiating event could lead into a series of steps that could ultimately lead to dam failure. This is an example taken in a book by Hartford and Becker, and this looks at an earthquake event, and then if the gates are operable, there's not going to be any problem, there's no reason to do any more analysis, but if the gates are closed and they're not operable, then there's a probability of losing the control of the reservoir, and that may lead to dam failure by overtopping. Now, there are certain rules that one has to follow in this sort of event tree analysis. The main rule is that whenever you branch out, the events that you define should be mutually exclusive and collectively exhaustive. Okay, that's a very fancy term, but basically means that they have to cover all possible cases and they cannot have any sort of overlap. So the sum of the probabilities of these branches should always add up to 1. And then this failure probability is calculated by taking these failed end branches by multiplying all the numbers that lead to that branch. How these probabilities are calculated, some of them are calculated through statistics, some of them are calculated through analysis like form and SORM and Monte Carlo simulations, but many of them have to be decided by judgment of the experts. So to run an event tree analysis, you have to run a workshop. Usually for a dam, you need at least a week to go through all the documentation, and then you have to discuss, every time you come to a branch, what sort of probabilities you have in your branching. And this requires translating verbal descriptions of probability into numerical descriptions. This is not a final answer, but this is now what we've been using in Norway in the last series of dam risk assessments. When we did this in 1996, we had fixed numbers here. So virtually impossible, then we would assign a probability of 1 in 1,000, 0.001. Very unlikely was 1%. Unlikely was 10%. Completely unknown was 50-50. But now in the recent round, and because this type of problem has also been discussed a lot in IPCC with the climate change and how you can quantify your uncertainty in the judgments, we're working with ranges now. So virtually impossible is almost 0 to about 5 in 1,000. Very unlikely from that to about 2%. And this also allows us that when we finish with the event tree, we can convert it into a Bayesian tree and go through a Monte Carlo simulation and get a range of the failure probabilities. So instead of ending up with one number, we end up with a range of probability of the probabilities. Now, when we looked at this dam in 1996, we looked at 2 sets of scenarios. One set was weaknesses in the dam, things like internal erosion, slides in upstream or downstream, operator error, and also a set of external triggers. When you go through this event tree, you have to first go through whatever scenario comes to your head. So we also thought about meteor impact, plane crash, nothing is too exotic. But then you have to choose which one of them do you want to use your time in the workshop. So the ones that are shown in bold here, these are the ones that were actually analyzed in the workshop. Now, this dam, even though the dam itself is a very robust structure, the spillway is right here, and this is how it looked like in 1996. There's a channel here, the approach channel, and then there's a spillway tunnel entrance, and then the water goes through that tunnel and goes through the other side. Now, remember that Norway is an Arctic country, and in winter time, this spillway could be blocked by ice and packed snow. This is a picture of the dam in end of March year 2000. My question is, where is the dam? The dam is here, and where's the tunnel? Where's the spillway? You can't see it. It's completely covered. And the reason they didn't think about this is that in the design, when they were designing this thing, the designing flood they assumed that it would happen in spring or in fall, when there's no snow. But actually, in winters, you could suddenly get a warm front with lots of rain and lots of snow melt. And then if that happens, then the water has nowhere to go. So that represents a very critical situation for this dam. So when we went through those inventories, the one that came up with the highest annual failure probability was this event here with overtopping due to clogging of the spillway and tunnel with hard snow and ice. And that gave an annual failure probability of more than 10 to the minus 3. This is not acceptable by any international standard. I mean, when your dam is a very important structure, the consequences of failure are very large, so you would like that number to be definitely less than 10 to the minus 4 per year. So they did a series of rehabilitations, and among those was building a new spillway, and they also built a structure to keep the spillway open during the snowy and windy winter season. This didn't cost that much, maybe a couple of $100,000, but that's really not that much money for this type of structure. But it was very effective. This is a picture of the same place in March 2012. Now you have this structure covering the entrance to the spillway. And you can see the entrance to the tunnel here. For scale, we have a Norwegian sanded here, so he's about 2 meters. It's typical Norwegian heights. So you can imagine that this thing is going to function quite well. And again, this picture that you saw from end of March 2000, in 2015 was also a very harsh winter, and now this is what it looked like in 2015. We redid the analysis last year for this dam. There's risk assessment, and the number that you saw, 5 times 10 to the minus 3, is now 2 times 10 to the minus 7. So just by identifying that critical failure mode and then investing a relatively minor amount of investment, we managed to basically eliminate that as a critical failure mode for this dam. But now some philosophical problems with reliability-based design. Risk acceptance. How much risk is acceptable? Well, conceptually, this is a simple problem. If we say that risk is a function of hazard and consequence, obviously, if you have an event which has a very low probability of occurrence, and if it happens, it has very small consequences, then the risk is small and it's acceptable. On the other hand, if there's an event which has a very high probability of occurrence, and if it happens, the consequences are catastrophic, obviously the risk is very high, it's not acceptable. And somewhere in this space, there's a line or there's a curve or there's a zone that separates the safe zone from the unsafe zone. The problem starts when you start putting numbers on these horizontal and vertical scales. But also an associated question with how much risk is acceptable is how much risk are we willing to accept. And that depends very much if the event is voluntary or if it's imposed. In voluntary activities, people are willing to expose themselves to extremely high risks. But if it's exposed by an external agent, then the tolerance goes down quite a bit. Now, Ken Ho from the Geotechnical Engineering Office, I think is in the audience somewhere here, he put together all the criteria he could find on risk acceptability from the different countries in the world. And he made this plot that shows the annual failure probability on the vertical scale and the expected number of fatalities on the horizontal scale. To interpret this curve, it means that if you have an event which can potentially kill one person, then you would like the annual probability of that event to be less than 10⁻�3. And you can see all these criteria start more or less at the same level. But once you get to these large events, which can potentially kill hundreds of people, there's about 4 or 5 orders of magnitude difference between risk acceptability with different criteria. And some of these criteria, when you plot them on this scale, they look a little bit strange. For example, it seems that in Belgium, if an event kills less than 10 people, it's acceptable. But that's not what it's meant. That's because in that code, they define disaster as some event that kills more than 10 people. So, but I'll show you an example of how that sort of risk acceptability criteria can guide us in designing some mitigation measures. The example that I chose here is Osoy Dam on Lake Sarez in Tajikistan. Even though Osoy Dam is the highest dam in the world, very few people have heard about it. I think even here among the geotechnical engineers, I would be surprised if more than 1% of you have heard of this Osoy Dam. And the reason is that it's not an engineered dam. It was created in 1911 by a large earthquake, which caused a massive rock slide that blocked the flow of the Morghab River. And these landslide-created dams, they're very dangerous. About 99% of them fail within 1 year. But this one was so massive that even after 100 years, it's still there, and there's no question of this thing failing. Just to show you how big it is, the Bennett Dam in North America is one of the largest dams in North America. It used to be the largest one, but I think now it's number 3. It's about 180 meters high. If you take the Bennett Dam and put it inside the Osoy Dam, this is what it looks like. And I guess you all have a concept of how high the Eiffel Tower is. You can easily fit 2 Eiffel Towers within the Osoy Dam. So the dam itself is huge. But the problem is that there's no spillway. The water has nowhere to go. So water has been impounding behind this dam for over 100 years. And right now, the lake that's created there, Lake Sarez, holds about 17 cubic kilometers of water. So if this dam were to fail, the resulting flood would be one of those catastrophes that is really inconceivable. There have been a number of studies in recent years on the safety of this dam and different disaster scenarios. The most realistic disaster scenario is that there's an active landslide on the right bank of the dam. And that's moving at the rate of a couple of centimeters a year. If suddenly this landslide fails catastrophically into this lake, it would create an impact wave or a tsunami that would overtop the dam, and that flood would kill many people downstream. So this is the more or less the boundary of the landslide. It's about 2 kilometers wide and about 800 meters high. There's a group that did a quantitative risk assessment for this scenario. Their assessment was that the annual probability of that event happening was about 10 to the minus 4. Remember that this is a very seismically active area, so the most likely trigger would be a big earthquake like the one that created the Osoy Dam to begin with. And if it happens, the resulting flood could potentially kill about 3,000 to 4,000 people downstream. If you plot that on this plot of acceptable risk criteria, it falls outside everything that's acceptable. Because of that, there's a very sophisticated early warning system that's been designed here that monitors many things and gives warning, and it's been tested now, and people are quite familiar with it. With the early warning system that's been installed, that point is now moved to this yellow point here. You can see the early warning system doesn't do anything with the hazard. The annual probability is still the same. What it does is that it moves people out of the harm's way. So you're moving horizontally on this axis. You can say now we have a situation which may be marginally acceptable, but still we would like it to have it lower. The next step would be to do something on the vertical scale, to drop this point down. And the thing that can be done is to build a tunnel there to reduce the level of the water in the reservoir. If that is done, then you would come to this green spot here, and the dam can be say, okay, now the risk is so low that we can forget about it. Unfortunately, I think this project, I mean, the early warning system has been installed, but the building of the tunnel, I doubt it very much it would ever be realized, because it's cost a lot of money, and the area is very inaccessible, and you know, Tajikistan has a lot of financial problems, and this is not the highest on the priority. Now, some challenges. We talked about quantitative risk assessment and acceptable risk concept. I think that's all nice and fine as long as we're dealing in this part of the curve. Once we get to these extreme events, which have a very low probability, but very high consequence, so-called extreme events, we're really dealing with a mathematical problem, which is 0 times infinity, very ill-behaved. And the question is, can we really calculate events? Can we really calculate probabilities with 10 to the minus 9, 10 to the minus 10 per year? Just remember, Earth is only 4 billion years old. So something is 10 to the minus 10 per year. It hasn't had a chance to happen yet during the whole Earth's lifetime. So if we end up here, maybe we should need a new approach, a different approach to the problem. So in recent years, people are increasingly realizing that this quantitative risk assessment and reliability-based design, it goes quite a far way for traditional engineering problems, but it's not maybe ideal for dealing with low-frequency, high-impact events. Since I'm running out of time and you're probably worried about your gala dinner, I'll try to go quickly. What's coming up now is stress testing. And this focus of stress testing is not on calculating these low probabilities, but on focusing on the system performance and identifying where are the weaknesses in the system, how we can make the system more robust. For example, if you think about the dam, the example I showed you, through that event tree analysis, we identified the weakness of that system was this entrance to the spillway tunnel that was being covered by snow, and then we could build that cover to make it more robust. After the Great East Japan earthquake in 2011, the West European nuclear regulatory agencies, they required stress testing of all nuclear power plants in Europe. And in terms of geotechnical engineering, Li Minjiang and his colleagues, they've proposed a framework for doing stress testing for Hong Kong slope safety system, and I think it's a very interesting paper. If you go through these steps here, you can see that it's nowhere in these steps he talks about any probabilities. The focus is on the system, where are the weaknesses in the system, what we can do to make the system more robust. But there are challenges, major challenges. What scenarios do you test for? If you're testing for an earthquake scenario in Japan, this is maybe the extreme event you test for. If you're testing for an earthquake event in Norway, maybe this is the event you test for. There are also some complicating factors and emerging issues. Urbanization, changes in demography is increasing the exposure of population in urban areas. Climate change is changing the geographical distribution and frequency and intensity of events like landslides, floods, and so on. And these cascading hazards and multi-risks and combination of natural hazards and industrial events like the one that we had in Japan, big earthquake leading to a tsunami, leading to an accident in a nuclear power plant, and so on. These are, again, issues which are challenging, but very interesting, and this is the way that research is going. So, in conclusion, deterministic analysis and design, they give an impression of certainty. Probabilistic analysis and reliability-based design complete the picture by making explicit the uncertainties and their effects. And for robust geotechnical design, we need both. Thank you for your attention.